So there's a couple equations we need to solve this problem. First, we have the inertia of a hoop, which is what this orbit is equal to the mass times the radius squared. We also need to know that the angular velocity is equal to the angular speed, is equal to the velocity over the radius. So we need to set our first side equal to our second side. So we need to have where it's closest to Pluto equal to where it's furthest to Pluto. So we plug in these two equations into our inertia times our angular speed. We have your mass times your radius squared times your velocity over your radius. One of these radiuses this radius can cancel and one of these can cancel. So you're left with your mass times your radius 1 times your velocity 1 is equal to your mass times your second radius times your second velocity. The masses can cancel because they're the same. You're solving for your second velocity where it's furthest from Pluto. So we have V2 is equal to R1 times V1 over R2. Plug in your numbers. You have 6.0 times 10 to the 6th times 9,000. And this is your radius where it's closest to Pluto times your velocity when it's closest to Pluto over your radius when it's furthest from Pluto, which is 2.0 times 10 to the 7th. Solve for that and you get 2,700 meters per second, and that's your velocity whenever the satellite is furthest from Pluto on this side.